Hello, today it's my pleasure to talk about binary 64-bit floating point systems. If you haven't seen my decimal floating point system video, be sure that you look at that. We looked at a quadratic polynomial there, wondering whether certain x's were going to be roots to within floating point error. And today we're going to look at an IEEE 64-bit binary floating point system. The IEEE standard came out, I think, in 1985. We're going to look at some round-off error near one of the roots of that quadratic. So here's the quadratic. It's a constant term of 1, a linear coefficient of -4, and a quadratic coefficient of 3. And we know that theoretically the perfect roots are 1/3 and 1. We know that. We're going to extend our view of that that we had in the decimal floating point system video. We're going to extend that to now looking at that first root here with the 64-bit binary. Okay, so we're wondering whether some given x is a root or not, and here's to within floating point error, and here's kind of the test for that is, we look at the absolute value of the absolute error. That's pretty tough to say, but that's what this is representing. There's a floating point calculation that we do, and then there's a true value that we have. And we want to know if the difference there is less than or equal to some bound. Okay, so if we're wondering if a particular x root is a root, then we assume that the true value is 0, and then the test becomes whether the floating point calculation of the polynomial absolute value, whether the floating point calculation of that polynomial is less than or equal to this bound. And so you want to make sure that you check out the other video to see where this bound comes from. But it's going to be it's another polynomial where the coefficients and the x's are all absoluted, and then there's going to be some integer coefficients that go in front here, and then you have that polynomial, multiplied by the machine epsilon. Okay, so we looked at it from the 2-digit decimal floating point and 3-digit decimal floating point system. Now we're going to look at it from the 64-bit. All right, so just a real quick review of the decimal floating point systems. I wanted to focus on normalization and what that means. Okay, here's our floating point, two decimal digit floating point system, where we've got a first digit, and then a decimal point, and then a second digit, and then we're multiplying by 10 to some power. So the D1 is decimal, so you can have let me say the D2 decimal digit, and you can have 0 all the way to 9. But D1 cannot be 0, so it's going to be 1 through 9. So I wanted to make sure that I clarified that with you. And then S1 is going to be the sign of the number, either +1 or -1. And then E0 is an exponent, and it can go from -9 all the way to +9. Okay, so we say this is a rounding system, and if we were to float 104, it would round down to 1.0 times 10 to the 2. If it's 105 that we're floating, then it's going to round up to 1.1 times 10 to the 2. And the machine epsilon here is 0.05, so it's 1/2 of the tenths place. And we called this F2. So the takeaway here, sort of the new thing I wanted to emphasize, is that D1 cannot be 0. It has to be 1, 2, 3, all the way up to 9. So it has to be one of those. And then it's normalized. And the implication of that is that you're going to have a hole between -1 times 10 to the 9th and plus 1 times 10 to the 9. So they call that an underflow hole, and it's going to be where you can't represent something over in that area. That's as opposed to anything that is above 9.9 times 10 to the 9 or below 9.9 times 10 to the 9. That's an overflow. So you have an underflow, which is near 0, and then you have an overflow that's a huge number. All right, so I actually had an error in my float 2 code. Hopefully everyone's looking at my day 4 version of this. And what the error was is, you go through and you get your exponent and your significand, you get those fine. But if it's an overflow situation where the exponent is bigger than 9, then you need to clamp it in that way. Make the significand 9.9 and the exponent 9. So I think the sign will take care of itself because it's already coming in. You've already set the sign, and then it never changes. And then if it were negative, then you make the x positive for the purposes of finishing out the function. Okay, so big overflow is handled properly. Initially, I had 9.99, but that's wrong. It's a 2-digit thing. So I've got to make sure I get 9.9 in the right exponent. So that's overflow. Underflow is when the exponent is very, very small, and from these calculations, it ends up looking like it's less than -9. In that case, you want to make sure that your significand is 1.0, and then you make your exponent the -9, and that's the smallest number as you can represent before. And I think this is instructive, that I emphasize that what I had before was wrong, and I'm explaining why. There should be a hole there, and I had a 0 and 0 there, and that can't be right. So now we're consistent with the way that this thing is supposed to work that was for the 2-digit decimal system. Okay, and then 3-digit is a similar kind of thing. In there, you're just adding another D3 and a D. It's kind of like D2. It could be 0 to 9, but D1 can be 1, can't be 0, 1 through 9. So similar kind of thing, and then rounding happens the same kind of way. And then the machine epsilon is half of the hundredths place. We call that F3. Okay. Now, are you ready? I hope you're ready for a binary discussion. So you've got 64 bits, and that is the data for a double floating point number. Okay, just like it's set up in MATLAB, and we're going to take that in MATLAB and kind of bust it apart and make sure that it makes sense. But it's 64 bits. Then, and what they do is they show this is actually the highest bit is a sign bit, and then there's 11 bits for an exponent. I'm going to kind of tweak this in a minute, but there's the sign bit is the very highest bit of the floating point, the 64-bit floating point number, so that's easy to get. There's 11 bits that's going to represent our exponent, and then the lower 52 bits is going to be the mantissa, which I'm using mantissa instead of significand, and there'll be a particular reason for that. I don't want to call this a signed exponent. I'll show you why in a minute, but I'm a little concerned about that. What I do is actually would like to bring in what I got from Google. So it confirms what I know. If you start at 0 and go up to 51, that's going to be your mantissa, or the fraction, you can think of it. Okay, because here's kind of a little bit of a gotcha, and this is a little bit of something that might kind of make you uneasy, but there's a hidden 1 that leads all of these bits. Okay, there's a hidden 1, so there's always this 1, so it's normalized with that leading 1. So we don't have to worry about making sure that one of the bits would be 1. We know we have this 1 there that's not represented in the bits, but that 1 is a hidden bit that is there. So it's 1 point, and then you've got your 52 bits, 0 to 51, and that's going to be your fractional part of your mantissa. So sometimes we'll show a little subscript there when we're trying to identify what the base is. And here I'm showing the base as base 2. So that's what that subscript means. Okay, and then these numbers here going from 52 to 62, that's an 11-bit exponent, and it's biased. It's a biased exponent. Really, I want to say that exponent is actually unsigned. It's you nominally you can think of it as 1 going to 2046, but the real value you have is biased, so you have to think about subtracting off 1023. So this is like 1023 is, what is it? That's 2 to the 10th minus 1. That's what that is, and then 2047 is 2 to the 11th minus 1. So we're looking at 11 bits of resolution on this biased exponent, and typically the biased, the E, will go between 1 and 2046, and if E happens to be 1023, then that means you're going to have 2 to E 1023 minus 1020. That's going to be 2 to the 0, which would be 1. So that's kind of our nominal position there, is when E is 1023. Then there's some special case where E is 0 or E is 2047. So 2047 kind of helps you when you get a huge number. So it kind of lets you represent infinity. So that's 1. And then when E is 0, that's a very, very special case I won't really talk about with you, but that's a subnormal. So we won't concern ourselves for that. So for us, typically E is going to be between 1 and 2046. All right, so hopefully you're getting a little bit of a feel for, there's some bits out there that's part of this double float, and we could, mask. We're going to go in and mask off the bit so we can see the mantissa or the fraction. We can see what the exponent is. And then the sign is a very simple thing. The sign is either 0 or 1. Well, if it's 0, that's going to be positive, because if you put the 0, you have that sign bit, you think about minus 1 to the 0, well, that's just 1, right? So that's a positive number, is going to have a sign bit of 1. And if it's a negative number, then that sign bit would be set, and then you would have minus 1 to the 1, or minus 1, multiplying all this. So I've kind of given you, a big picture of, the 3 pieces of a floating point number, binary in this case. You got your fraction, and that's binary. And then you got your exponent, that's biased, and also binary. And then you got your sign bit, okay? Really good slide here. All right, so kind of want to put it in the same format that I had earlier with the decimal type system. So we've got, our S is going to be 0 or 1, sign bit. Our M is the mantissa, and we can think about it this way. We can think about that hidden 1 kind of snuck over here, but our M is going to be our 52-bit mantissa. And if I had that, if I had that M, I could think about, in this representation, dividing it by 2 to the 52 power, and then adding that to 1, and then multiplying by 2, and then you've got that biased exponent, E minus the bias. Okay, so that represents how the 3 pieces would kind of give you back that floating point number. So let me look at some examples here with you. Just very simple example is, hey, how do I show the floating point value of 1? Well, it's going to have a 0 mantissa. It's got a 0 sign, and the biased exponent E is 1023. Okay, so those are your three pieces. And then I just kind of arbitrarily thought about, what if I said, okay, I'm going to have a Mantissa of 4,000. What does that look like? So if I have a Mantissa of 4,000 and a signed bit of 0, exponent of 1023 again, well, here's what it looks like. I end up with something that has a little bit of fuzz here, way to the right of the decimal point. So I still have the 1, and then way to the right of the decimal point, I start picking up some decimal digits that represent that 4,000. Okay, and if I were to think about, well, what's the smallest Mantissa I can have? Well, that's going to be 1. 1's the smallest Mantissa. That would be, obviously non-zero. So if I were to do that and look at that represent same exponent here, the 1023. So I'm going to get the value with all the way. I think this is like in the 15th or 16th place. You're going to pick up that 2. Okay, so that's kind of an introduction over kind of what the pieces are, and I'm going to bust out some of my. Okay, if I can sneak my MATLAB in here, my day 4, I'm going to have my float 64B at my disposal, and I thought, well, let me do a couple of examples with you here. So I'm going to do my global debug 1 and set that. So you can see what the individual pieces are and the masking. Okay, so I'm going to go float 64B. Let's do 1, just the value 1. No semicolon, because I'm going to see what it returns. Okay, so it returns a 0 sign, a zero bit for the sign, a 0 Mantissa, as we were thinking about over here, and the exponent is 1023. That's the bias exponent. Okay, so let's take a look at kind of the pieces. So the actual integer 64-bit of 1, it looks like this. The lower 13 nibbles represent the Mantissa. 3 fox, that is the biased exponent. So that 3 fox is going to be 1 less than 400. So 400 is 2 to the 10th power. So it's 2 to the 10th power minus 1. 2 to the 10th power is 1024. So it's 1 under that. So I see that. I'm very comfortable with that. And the highest bit is actually 0. You can see the highest bit of that nibble would be 0. So this is showing you the masks. So if you look at the code, it will use those masks on the actual 64-bit representation of your decimal number or your double floating point number. Okay, and then the Mantissa is being masked with those nibbles. So again, we got 0. We're masking 0, so we're getting 0. And then when we're looking at the exponent, we're using that to mask, and that's how we got the 3F or the 1023. So that's how it works. Clear command. Let me do a float 64B. Let me do the next one, which is 1 plus, and then the next one has 4,000 divided by 252. So let's give that a shot. 4,000 decimal divided by 2 to the 52 power. Let's see what that looks like. Okay, so the Mantissa is 4,000 decimal. That's what we thought there. Hex-wise, it's got a Fox Able 0 in the last 3 nibbles. So that Fox Able 0, that must be 4,000. The hexadecimal version of 4,000. We got that from masking the mantissa there. Same exponent that we had before, the 1023. Okay, so let me clear command. I want to do the last one on this page. It's going to be float of 1 plus 1 is the very float 64b of 1 plus 1 plus 1 divided by 2 to the 52 power. Okay, see what that is. All right, so you see that the mantissa has that 1, and that's as small as you can go right there, having that 1 out there. Same exponent. Mantissa's 1, mantissa's 1. So that's what it looks like. And then when you look at, when you unravel it, you end up with that 2 all the way over there. So this looks like, if I do EPS, there's a 2, that 2, I think, and that's 2 to the e to the minus 16. So I think, I'm going to clear command. What if I did a float 64b of 1 plus EPS? So this EPS is what they're claiming the double floating point machine precision, or epsilon, is. Let's see what that gives me. Yeah, so that's what it was. It gives you that 1 for the mantissa. Okay, sign 0, same exponent. Okay, so that's interesting. Let's do something a little more interesting as well. Float 64b. Let me do pi. See what that looks like. It's always fun to do pi. All right, so you see pi. We've got a lot of mantissa stuff here. So you use the mantissa mask in order to pull off that value there. The exponent is going to be 400, so that's 4. That's 256 to the 4, so that's 1024. Right? 4 times 256, so that's 1024. And then this hexadecimal mantissa looks like that in decimal. So very interesting. And then if I were to look at that mantissa in a hex, switching that 4000, that's what it was. We saw that in MATLAB. Okay, so this is the code that I just called up with the float 64b. Look at my actual code, because it shows the printing with the debug. My real file has a debug capability, but you're creating this mantissa mask by taking 1 and shifting it to the left 52 places and then subtracting 1. That's what gives us the 13 Fox nibbles that we're going to use for the mask. The sign is taking that 1 and shifting it over 63, and that's going to just pull off that very high bit of the 64-bit double float. And then the exponent mask is a little bit tricky. How I did it is I basically took a minus 1, a 64-bit representation of minus 1, which would be all F's, and then I did a bitwise mask of that with a bitwise complement of the OR of the previous 2 masks. So I did an OR, bitwise OR of these 2 masks, so that kind of would glue them together. Would take the highest sign bit and then the 13 nibbles, and it would, do an OR, would kind of combine them. And then I did a complement of that. Okay, and then once I do a complement, it would give me 1s where the 0s were, and then I do a bitwise AND of all bits with that, and that's how I got the exponent mask. Now, I think I said all that right. So anyway, first thing you do is a bit AND with the IX. So the IX is a typecast. You're taking the X. You're not changing the X, but you're making it look like a 64-bit integer. So that's what the IX is that I print out earlier. So that's how you get the sign, with doing a sign mask on that. And then you do an exponent. You get the exponent from a bitwise AND of the IX with the exponent mask. But then you got to think about shifting it back down, because it's 52 is where that mask or the exponent starts. You want to get that kind of shifted all the way to 0 bit position. And then the mantissa is just a simple mask. So that's how the code works, to kind of pluck off things. So I think it's very important for you to kind of understand where these bits and pieces are coming from. Okay, so I want to think about running my script 64, focusing near that 1/3 root. Okay, so what happens is, if I were to bring in my, let me bring in my MATLAB here real quick. All right, so I'm going to clear command, and I'm interested in float 64b of 1/3, because I know 1/3 is the root a priori. So what happens is, when I bring 1/3, 1/3 looks like that. All right, so it's got a 1021 for the exponent, but really the fine detail is that the hex, it's like a continuation, just like it is in the decimal representation of 1/3. You have a continuation of the various bits. So here, the bits are 5 hex. So if you're looking at the mantissa part, you see that the one, there's all 5s right there. So that's looking like the 1/3 there. Okay, so let me clear command. So I could run. So this file came from my script 64 run. So let me do that. Script 64 of my in my day 4. See what that does. Oops. Okay. So I should have turned debug off. Okay, with debug off, let me rerun script 64. So it's going to look around the area of 1/3, and it just ran a bunch. I think it ran like 4,000 different x values near 1/3. Check that out in a minute, but you can see that in the PowerPoint here, I've taken a little bit of a snippet of all of the possibilities. And what I do is, all the way on the right, is I show whether it's thought to be a root, and most of these are not. Most of these definitely, very, very few out of, I think it's 4,000 points that I check near 1/3. So I'm getting near that 1/3 value. Remember, that's where my hex or digits and the mantissa are all 5. That's going to be the perfect 1/3, or perfect, closest representation of 1/3 as you can get. So I'm honing in now. Let me see over here. So it's not thinking it's a root still. Oh, right there is where the root turns off. Okay. Kind of sneak this out so I can see more. So it's there. So that looks like decimals. I've got not 33, but I've got a 40. And not 5 5s. I've got a 5 6 2. And then, of course, the 5 5s, that's still 1. So that's the decimal representation. That is as close to 1/3 as I can get. Hexadecimal, close to 1/3 as I can get. And the floating point error from the polynomial is exactly 0. It's exactly 0 there, too. So that is the Horner representation. Here's the error bound. I'll show you in a second how I get that. And then just kind of going backwards towards the beginning, his root starts at about 27 on the rightmost decimals in 4a. Okay, but here in the screen now, I'm showing just kind of a very small snippet around 1/3. Those are the ones I think that are going to give me the true root, or say that not the true root, I beg your pardon. That's going to give me that these decimal values are roots to within floating point error. Okay, that's precisely right. So it says that the floating point floating point calculation from the Horner sequence is less than the error. So you can see here I'm 13, that's less than 14 there, all the way on the right. And of course there were two, and we're looking at this root right here, the 1/3. But there were two that gave me the perfect Horner. The Horner gave me the perfect 0 there, close to 0 as possible. I thought it might be good, instructive to sneak a peek at my script 64, and I kind of want to walk you through how it works. So remember that the constant coefficient is 1, the linear coefficient -4, and the quadratic coefficient is 3. And what I do is just kind of like I did in the 2 decimal digit and the 3 decimal digit version. I brought those in as structs, so I did the 64-bit float 64B of those double values, and I got the struct versions of them. So I have that, and then I went ahead and I wanted to find about where to start. Okay, a little bit clunky here in my description, but I gave myself a structure of representing that 1/3. Remember that has all the 5s in the mantissa, but I wanted to kind of start there, and it actually will print out what the root is. What I wanted to do is I wanted to get that mantissa, and I wanted to offset it. So I subtract 2000 from the mantissa, and then in my for loop, if you see, my for loop starts at that shifted mantissa, so I'm starting before the 1/3, and then I'm going to go 4000 as fine as I can get, just adding 1 to the mantissa on every time through the for loop. Okay, every time. So this is as fine as I can get. I'm bit fiddling down there at the mantissa level. And when I do that, I'm able to cover that whole span, because I'm doing the for loop from 1 to 4000. So I'm starting with a mantissa that is 2000 below where 1/3 is, and then I'm going to increment the mantissa in the for loop 4000 times. So eventually I will cover the 1/3 location, and it'll be about in the middle is how it works. So that should be straightforward. So I get the mantissa, and then I unfloat it or unravel it so that I can store it into my array. So I'll have an array of x's. And here, this part here is like I did in my floating point examples video. Okay. Is where I brute forced the Horner sequence. So I take the A2, the highest coefficient, multiplied by x. So that's the first thing, is that product. And then the second thing is I take that's my P1. I take that P1 and add to it the A1, the linear coefficient. And these are all structures, and they return structures. So I add that, I get an S2S, and then the S2S I multiply by x again, right? So it's a multiply, sum kind of thing. And the very last thing is I take that P3 and I add in the constant term. So there's the 4 operations for the Horner Horner sequence for the quadratic. Okay, so S4S is the Horner representation of the value or the calculation of the polynomial. Okay, so we want to see if S4S is going to be less than that floating point error bound. So here's the floating point error bound. I take and create that polynomial with everything absoluted, and then I've got these various coefficients that are 3 and 4 in the case of the quadratic. I take that same thing and multiply by EPS, and that's going to be my error. I called it error, all right? So listed as max error here, but I want to see if the floating point, the unraveled floating point of that last step is going to be between minus error and plus error, right? So, and I kind of keep my S4S is signed. I could take absolute of it, but I keep it as signed just so I can see how that progresses. And then I just want to walk you through what this is doing here. The fprintf. So the fprintf, there's a formatting string here. Okay, formatting string, and then there's the variables, and these variables kind of slot with whatever the percent. So the percent is a character in the fprintf that says, hey, I'm going to format something here. So the first thing is the X, the double X that you're going to print, and that's what I'm printing right here, and it's printing it with 16 digits to the right of the decimal. So that's what the .16f F means. It's a double float. And then it's going to show a percent %s. So the percent %s is a string, character string, and that's coming from this bit here. So it's taking the mantissa, my current mantissa, and it says, okay, give me 13. It's taking that decimal and giving me 13 hex digits. And that's a character string, character array. And I'm going to kind of give it that my happy prefix of 0x. So that's what's printing here. And then the next one, I'm just kind of walking through them. The next one is, hey, I want 16 digits past the decimal point. I've got a double float. So the double float is going to be the unraveled of that last sum. So that's the result of the Horner calculation. All right. And that's going to be a signed version. Remember, I said I wanted to keep it signed so that I can see it. And here, that plus in front of the dot means, yeah, show me the sign, whether it's plus or minus. And that's what it's doing. And I do that so that, things are staying aligned so that it prints out pretty. So you see even the positive ones have a plus in front of it. So if it didn't have that plus, it would show the negative, but the positive ones, it wouldn't show the plus, and things would get kind of shifted over. All right, then it's showing my error. The error is the max error, which came from that absoluted polynomial, and that's the bound. And you see here that the 13 absoluted would be less than the 14, so that's why it's a root. I like to print out this factor. Factor is the thing. It's the thing that multiplies EPS in the error. All right, so I like to print that out. So that's how many machine epsilons that you have in your sort of build up. So that's showing 6 machine operations. That's sort of the tolerance. That's how I look at it. And then the very last thing that's printed is root, and that's ZZ of the current iteration. So that's going to be a Boolean. That's going to be 0 or 1. 0 if it's not thought of as a root, and 1 if it's thought of as a root. So you can see how I get that. If the float of that last Horner operation, if it's greater than minus max error, remember this is signed. So you're kind of seeing if it's between minus max error and plus max error. That's what you're seeing there. And that and means that it has to be, both things have to be true in order for it to be a true root, or thought of as a root within floating point error. Okay, so I thought it would be good to show you, kind of walk you through how this works, and how we're bit fiddling minutely. All right, so the key summaries here. So we've taken a look at 64-bit floating point behavior here, sort of near a range of a root, the 1/3. And it's kind of the same thing, the same phenomena that we saw in the 2 decimal digit and the 3 decimal digit. You get this swath. Now here, obviously the swath is not that big, but you do get a swath where things appear to be a root to within floating point calculations. There was, in this example, there were 2 that kind of gave us a Horner of all zeros, right? But to be honest, you usually don't get that. You usually don't get that all zero kind of Horner thing. So it makes it tough when you're looking for roots. You have to have that real good understanding of, hey, this is going to be the best I can do. So normally it doesn't happen that you get that all zeros like we did. Okay, so that's why I'm trying to get you guys thinking in terms of is it a root kind of test. Okay, so that's all for today. I hope you thoroughly enjoyed that.